Dr. Castellana here. In this video, we're going to be talking about symmetry of equations. We're going to start first, though, by looking at points and their mirror images with respect to symmetry. The symmetric image of a point P through a given line L is a point P' that is on a line perpendicular to L, containing both P and P' and is the same distance from L as P, but on the other side of L. So here we have the line L, and we've got P on one side and P'. This dotted line here is perpendicular to L, and this hash mark and this hash mark are denoting that this distance here is the same as this distance here. So they're equally distant either side of L, both on a line that's perpendicular to L. So they're mirror images of each other through the line L. We also want to talk about symmetry with respect to a point. The symmetric image of a point P through a given point Q is a point P' that is on a line that contains both P and Q and is the same distance from Q as P is, but on the other side of Q. So here we've got all 3 points, P, Q, and P'. They're all on the same line. And this distance of the line segment from P to Q is the same as this distance from Q to P'. So P and P' are mirror images through Q. All right, so how does this relate to graphs? So a graph has a type of symmetry, be it symmetry through a line or symmetry through a point, if every point on that graph, for every point on its graph, its symmetric image is also on the graph. There are 3 basic types of symmetry that we are interested in when it comes to equations. Symmetry in the x-axis. So our symmetry line is going to be the x-axis. Every point above the x-axis will have a matching guy below the x-axis that is its symmetric image. Also, if you notice, if you were to take and fold this graph along the x-axis and fold the top half down over the bottom half, the 2 halves would match exactly. That's a good way of visually inspecting for symmetry. In the second type of symmetry we're interested in is symmetry in the y-axis. So both of these are symmetries with respect to lines. This time the y-axis is the symmetry line. For every point over here on the left, there's a matching point on the right. And if we were to fold this graph along the y-axis and fold the left half over onto the right half, they would match exactly. The final type of symmetry is a symmetry through a point. It's symmetry in the origin. So now the symmetry point is going to be the origin. Every point over here on this graph has a matching point on the other side of the origin. If you draw a line from this point through the origin and go the same distance you went to get the origin, past the origin, you would find a matching point. It's a little harder to visually see symmetry through the origin. A couple tricks to trying to determine if it's symmetry through the origin. One way is to rotate the graph 180 degrees, making the pivot point the origin. If that still looks the same as it did before the rotation, then you have symmetry through the origin. And an alternate way is to flip in the y-axis and then flip again in the x-axis. And after that double flipping, if you get back what you started with, you again have symmetry in the origin. All right, but what about if we don't have the graph to look at? Sometimes we want to use the symmetry, if we can determine it ahead of time, to help us draw the graph. Again, let's take a look at points first and look at things in terms of their coordinates and not just the geometry. If we look at a pair of symmetric points with symmetry in the y-axis, it follows that they will have the same y-coordinate and their x-coordinates will be opposite of each other. So when we look here, here's what's going on. Symmetry line is the y-axis. Both points have to be on a line perpendicular to the y-axis. That means it's going to be a horizontal line since the y-axis is vertical. Vertical lines, all of the points on them have the same y-coordinate. So both these guys have a y-coordinate of 3. At the center of this horizontal line is the y-axis. That has the x-coordinate 0. The point P in this example is 2 units to the right of that, so it has an x-coordinate of 2. The point P prime is 2 units to the left, so it has a x-coordinate of -2. One of the points is going to be to the right, and the other one is going to be the left, and those distances will be matching, so you will have a positive and a negative matching coordinate for the x-coordinate. We get a similar situation with points that are symmetric in the x-axis. In this case, they will have the same x-coordinate, and their y-coordinates will be opposite. Kind of the same idea. The x-axis is horizontal, so the perpendicular line that both points have to be on is vertical. Vertical lines, all the points have the same x-coordinate, so the x-coordinates will match. So this guy's got a 2, and this guy's got a 2. And here, just like we had the left and right distance, now we have up and down distance. This point is 3 units above, this point is 3 units below, and so it ends up being a -3. Points that are symmetric through the origin, these turn out to have both coordinates being opposite of each other. So this guy has the point x-coordinate 2, x-coordinate -2, x-coordinate 3, x-coordinate -3. This is a little harder to see why this happens. But a neat little trick is, if you take these 2 points and find their midpoint, that's going to be the point that's halfway between them on the line that connects them. It's the midpoint. Well, if you think about the definition of symmetry through a point, the symmetry point will always be the midpoint between the 2 points that are symmetric. Well, if I do take the midpoint between these two, I end up with 2 minus 2, which is 0 over 2 is 0, and 3 plus -3, which is 0 over 2, and which is 0. So the origin is the midpoint. So it will be the symmetry point. That happens anytime. If you take any point with coordinates x, y, and then you take the matching point -x, -y, the midpoint will always be the origin. So we can just negate both coordinates to get the symmetric image. Let's use this to check symmetry on some equations. So basically what we're going to be doing is taking the equation and replacing either x or y, or both x and y, with their negative counterpart and seeing if the equation matches. So to check the symmetry of the equation, 3x plus y squared equals 4. If I want to check to see if it's symmetric with respect to the x-axis, I'm going to replace y with -y. I get 3x plus -y squared, or the quantity of -y squared equals 4. That simplifies to 3x plus y squared equals 4. That does match the original equation, so I do have symmetry with respect to the x-axis. If I try to check for symmetry in the y-axis, I'm going to replace x with -x. This will give me 3 times -x plus y squared equals 4. That simplifies to -3x plus y squared equals 4. That does not match, so I do not have symmetry with respect to the y-axis. If I go on to check for symmetry with respect to the origin, I'm going to replace x with -x and y with -y. I get 3 times -x plus the quantity of -y squared equals 4. This simplifies to -3x plus y squared equals 4. Same guy we had over here. This is not an exact match, so we do not have symmetry with respect to the origin. One more example, just to make sure we've all got it. Let's check the equation y equals 4x cubed plus 2x. If I want to check for symmetry in the x-axis, again, I replace y with -y. That's just going to give me -y equals 4x cubed plus 2x. That does not match this guy, so I do not have symmetry in the x-axis. If I check for symmetry in the y-axis, I replace x with -x. That's y equals the quantity of -x cubed plus 2 times -x. Simplifying both of those gives me y equals -x cubed minus 2x. That does not match. It actually matches this guy over here if you multiply both sides through by -1. So we do not have symmetry with respect to the y-axis. Finally, checking for symmetry with respect to the origin, replace both x and y with their negative counterparts. So I end up with -y equals -x quantity cubed plus 2 times -x. Simplifying that, I get -y times -x cubed minus 2x. Multiplying both sides through by -1, I get my original equation back. So I do have symmetry with respect to the origin. Well, that's all we've got at the moment for symmetry with equations. Check in for the next video.